So where are we at? We're on Friday. Our goal today is to... No, okay, that's, yeah, thanks. That does not make sense. Our goal is to start 2.7, but if you realize we're also going to be continuing that next week and, in a sense, finishing it on Tuesdays. This is a 3-day section, guys. Ooh, nope. It's a 4-day section.
Oh, wow.
2.7 is intense. Not that it's impossible, and actually I think it's one of the easiest types of word problems that you'll see AP style, but there are lots of different things that can show up, lots of different reviews, just like area and volume formulas from geometry and stuff like that. So we're starting it today, but we're going to grade 2.6 first, hopefully get 2.5, 2.6 out of the way, and that way we can get ready for 2.7, and we'll be definitely finishing that next week. But just so you guys are planning ahead, when's our next test? Next Friday. Okay?
So we won't be doing 2.8?
We actually don't need to do 2.8. It is not covered by the AP. It doesn't mean that no college class ever would ever cover it. It just means the AP says it's not a topic that we need to focus on. All right, cool kids. So we're only going up to 2.7, but it is a 4-dayer. But it's really 3.5 because today we're actually still kind of finishing up 2.6. We're going to be grading. I have 2.6B answers ready to go, but let's go back to your workspace, okay? Here we go. You guys were working. You guys were collaborating in your groups. Let's make sure that you have a good idea of 2.6. For number 89, what did you guys do? Implicit or formula?
I tried
Tried to do formula and it got messy?
Yeah, she was.
Okay. I heard formula the most, so let's just try for formula. Sound good?
Yes, please.
Okay. You guys help me out. Formula. I'm talking about finding f prime, true?
Yes.
Okay. So then, for number 89, f prime of x needs what rule?
It is product.
Product rule. Now, hold on. Couldn't we rewrite this to be 2x times x minus 6 to the 1/2? Okay. So product rule says?
Second D first.
Second D first. Good. So that'd be x minus 6 to the 1/2. Derivative of the first is 2 plus first d second. What's the derivative of u to the 1/2?
1 over 2
Yeah.
square root of x minus 6.
It'd be 1/2, which is where the 1 over 2 comes from. X minus 6 to the negative 1/2, which is why it's in the denominator. And why is there not a u prime?
Because the derivative of x is 1.
Good, there is a u prime, but the derivative of x minus 6 is just 1. So times 1, there we go. Kiddos, if I were you, I'd definitely simplify this just a little bit, right? So we could do square root of x minus 6, put the 2 in front, plus these 2's will reduce, so we'll have x over the square root of x minus 6. And the nice thing is, we're just plugging in eventually, right? So let's just kind of leave it. That's our f prime. If we needed to make it look pretty, we could with a common denominator, but let's just leave it. Okay, now, what do we do with that 40?
We put it in the
Gotta plug it in for x, but at the inverse, so what do we have to do first?
first y's.
Good. So we can say 2y times the square root of y minus 6, and what are we putting here?
40.
Good. So switch the x and y, that's the inverse. Plug in the 40 for the x spot of the inverse. Solve?
I wanted to square both sides, but that just sucked.
You could square both sides, it would just be really nasty. But you could. If you did want to actually try to solve it, this one you could solve because you would get 400 equals 4y squared times y minus 6. Because you would square, it would be this multiplied by itself. At which point,
Set both of them.
no, you can't set both of them. That's only when you get a 0. You'd have to go ahead and distribute, get it all to one side, and try to factor polynomial factoring with testing zeros and synthetic division. You're going to be testing anyway. It would have been better just to plug in. Now, some people started plugging in and realized 1, 2, 3, 4, 5, 6 don't even, well, 1, 2, 3, 4, 5 don't even work. 6, well, that's going to be 0. So we know it's something higher. So 7, that's just 1 times 14. 8, that's just square root of 2 times, well, that's not nice. 9, 10, square root of 4 is 2. 2 times 20 is 40. So yeah, y equals 10. Now, I know it wasn't 0, 1, or 2. But it couldn't be any numbers up until 6 anyway. So you have to start at 6. 6, 7, 8, 9, 10 ends up working. And if you guys realize, 40 is a nice number. So 6 minus 6, square root of 0 is good. 7 minus 6, square root of 1 is good. But 8, 9, 10 was the next nice square root to make it nice and even. At which point, my formula says what? F inverse prime of 40 is 1 over, take this guy and plug in that guy, right? So it's going to be 2 square root of 10 minus 6 is going to be 4 plus 10 over square root of 10 minus 6. Square root of 4 is 2. 2 times 2 is 4. Square root of 4 is 2. 10 over 2 is 5. What's my final answer? Where'd you guys get stuck though? Because there were quite a few places.
It was finding the y. It was finding the y.
It was nasty because usually it's 0, 1, 2. And if you guys tried to solve, see how it just led us down this horrible spiral, down the rabbit hole. We're talking about Alice in Wonderland. So try plugging in, and you couldn't even do anything up until 6. So you had to start at 7, 7, 8, 9, 10. I know. Potter's rule is another place you could have gotten stuck, but that's review. Number 90. What rule do we use? Wait, arctan, what's that?
Ooh, tangent inverse.
Did you guys realize that in the homework?
Yep.
And the AP, actually on the first page before you even open it, like there's some little notes, and one of them is arc. Arc trig is the same thing as trig inverse. It just lets you know in their terminology, if there's arc sine, it's sine inverse. Arc cosine, cosine inverse. Arc tan, tan inverse. Means the same thing. So, who's your U?
X over 3.
There were multiple ways to find U prime. What did you guys find as your U prime? Could have done quotient rule. Could have done.
1/3.
Yeah. What's the other way than doing quotient rule?
Oh, I mean, you could wait.
Couldn't you rewrite this? Remember, if there's just a number in one of the numerator denominators, you can rewrite. X is actually, you could make 3 to the negative 1, but it might be nicer just to separate the x from the constant. So it's 1/3 x, because then you can just use power rule. But you could use quotient rule. Bottom to top would have been 3 times 1, minus top to bottom would have been 0, all over bottom squared, and you get 3 over 9, which is 1/3. Quotient rule works, but rewriting does also. Guys, that was just to get U and U prime. What's my formula for arctangent?
It's 1 over 1
Wait, why is there 1/3 here?
because that was before.
Yeah, because that was the coefficient, that was the constant. So I keep the 1/3. Now I'm doing 1 over 1 plus U squared. Well, U is x over 3, right? Times U prime, which was 1/3. It's getting kind of messy, so let me go ahead and move my U over here just to get out of the way. I'll struggle on the week, please. There we go. Okay. I'm going to simplify by, I would say simplifying the denominator, right? So 1/3 and 1/3 is 1/9. Then I get 1 over 1 plus x squared over 9.
Multiply it and...
Do you guys realize? Yeah, you already had your little 9. You didn't have to do top and bottom because this guy's going to come on in. So when I come on in, 9 times 1 will be
1 over 9.
9. And 9 times x squared over 9, the 9's cancel. You just have x squared. Final answer is
D.
D. And last but not least, when they say what is the slope, what should you always think of?
Derivative.
Well, I guess when they say what is the slope of the tangent, yeah, always take the derivative. Take it as is, just go for it. So derivative of f is, that's fun. No stress, right? Derivative of f is that fun. Taking derivative both sides. How to take the derivative of ln of u?
1 over u times u prime.
1 over u and u prime. Derivative of x cubed plus 1 is 3x squared. What's the derivative of arctan or tan inverse of u?
1 over 1 plus u squared times u prime.
And then what's u prime?
4.
All you have to do is plug in 1. I don't even know if we have to make it super spiffy or snazzy, so we'll do 3 times 1 squared all over 1 cubed plus 1. 1 over 1 plus 4 times 1 is 4. 4 squared is 16, but we'll get back to that. 3 over 2 plus 4 over 5? No, 17. 17. Sorry, I didn't square the 4. Whew, 17. And you get common denominators, right?
34.
Yeah, so times 17 over 17. 2 over 2. We end up with 51 plus 8.
59 over 34.
Spells add. Go team.
Woo!
Okay.
So on the exam, how long do you have like approximately for
1.2 minutes.
Really?
If you spent the exact same amount of time on all of
If
But,
you don't,
question,
then usually
it.
there's
Is this one a bit longer than that one?
Yes.
So,
I feel like it is equal.
1.2, roughly. Usually on the calculator portion, which is like 18, 20, 15. They just changed it last year. Sorry, it's not in my head yet. It used to be 17. The calculator portion, almost everyone finishes early. But it's really hard. And then the non-calculator section, almost everyone has to rush the last 2 or something. But there's enough time as long as you. What the guy who has, he's called Mr. Calculus. He teaches down in Diamond Bar. Basically, he's in a public school, and he went to the junior high that feeds into their school, and basically built up their math program. So pretty much all the kids are taking geometry by 8th grade, 7th grade, 8th grade. So that he has huge BC classes. Anyway, long story short, he tests his kids by giving them APs throughout the year that they're not ready for at all. He teaches them to go through the test and be like, ooh, this one's easy, I can do it, let's go. This one's not, and like how to mark it. So they go through and do all the easy ones first, they rock the easy ones, then they go back and do the medium ones, and then they leave the hard ones for the end. Because that way they maximize their time. The problem is you have to get really good at reading the questions quickly, or else you waste time going through and analyzing the test. So, it just depends. I say go through it in number order, and if you know it, go for it, and if you don't know it, skip it, come back. And if you know it and you go for it and it's not working, do your best educated guess and then come back. Just because you don't have time to agonize over one when you have 25 more to go. But anyway, good question. We're coming back to that in just a second. Kiddos, let's peek really quickly at these 2 examples. You can do them in your workspace if you want, or you can just watch me really fast. These are the 2 examples we did to yesterday that you were supposed to practice with your formulas last night. Is there a formula for cosecant inverse? You can put it in your notes, you can put it in your workspace, or you can just pay attention. I don't really care. There's a formula form. Does anybody have this one memorized? Ooh, Charlotte, go!
Okay, Matthew, 1 the square, no, the absolute value of u and this times the square root of u squared plus minus.
Times? The only one that has plus, good job. The only one that has plus is tangent and cotangent, inverses. So the only plus is tangent and cotangent, and they're weird because they don't have a square root anyway, so they're just weird. And if you think about it, it's because opposite and adjacent Pythagorean theorem, it's squared plus squared in order to get it. Anyway, tangent and cotangent, but all the rest have subtraction. Secant and cosecant inverses are weird because they have the absolute value and the order is switched. But otherwise, it's minus, just like sine inverse, cosine inverse. So guys, if we just plug in, wouldn't this just be f prime is equal to -1 over absolute value of 5x square root of 25x squared minus 1 times 5?
Yeah.
Can you, this is why I have this example, can you simplify?
Yes. You can have some fun.
No, I wouldn't.
Why are you allowed to reduce the 5s even though one of them is in the absolute value?
Because they're positive.
Yeah, it's a positive 5. We could technically, to make it all legal, we could technically pull the 5 out of the absolute value, because guys, does the 5 make any difference as to whether or not the signs change? No. 5 is just 5. These are positive times it. So I can pull the 5 out. Sometimes it's going to be a little tricky when you guys go to think about, can I reduce with absolute values? It's going to be a bit of a process. Every now and then you'll get stuck. You just need to ask if you're not understanding when you try to make it match in homework answers, etc. Okay? So let me know, but yes, these 5s do reduce. So your final answer would just be -1 over. We have to keep the absolute value because that x can be negative. So I need to say no, 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 stay positive. Hey, life lesson. Anyway. Does that make sense? Plug in and check it. Does it make sense why the 5's reduced? Last one. We did one of these nicely in your workspace, so maybe you guys are good. But when it says find the slope, what does it say to do? Don't plug in. Take the derivative. And since there's stuff on either side, we're just going for both sides, right? So we'd have to take the derivative of both sides. What rule? Products. Why? Read it. X times arctangent. X times tangent inverse. So second would be arctan. D first plus first. Ooh, derivative of arctan? 1 over
1 plus
u squared times, oh, what's u prime if it's x?
1.
Oh, that's easy. So second d first plus first d second equals, what's the derivative of e to the u?
E to the u times u prime dy dx.
Good. Do I need to get dy dx alone first? I guess. But what are you doing anyway?
We're plugging in.
Technically you could just plug in. So plug in 1. This one's fun to simplify. So much pre-cal and one problem. What's arctangent of 1?
Obviously that's a unit circle.
It's a unit circle. It is at 45, and specifically pi over 4. Because, what's the sine and cosine of pi over 4? Root 2 over 2 sine over root 2 over 2 cosine. So pi over 4 is the angle that gives us the sine over cosine that reduces to be 1. Remember, going backwards. You guys remember why I put the unit circle in the forever cards? You could know all the calculus and get to the last step and be stuck if you don't know it. That's a bummer. Then 1 over 1 plus 1 squared, isn't that just 1/2? And over here, what happens to e to the ln? More pre-cal. Cancels out, you just get... Ah! I'm going to solve for dy dx.
Divide.
Sure, or multiply by the reciprocal.
Distribute.
That's just going to be 1, right? 1 plus the 4 and the 2 becomes, is it 2 over pi? So the tangent line is 1 plus 2 over pi. Could you rewrite that to be pi plus 2 over pi? Sure. Could you rewrite it to be 2 over pi plus 1? I don't know. I'm making up stuff now. Yes. Alright, section 2.6b, done. Let's go ahead and grab out your, open up in your homework spirals to homework. If you don't have it due today, please catch up this weekend because this next section is a beast. We're going to take 4 days on it. So you want to be caught up.
When it says due tomorrow.
Oh, I didn't update the board. That's the one that was on there yesterday. Alright, kiddos, as you are grading, I'm going to come around to look at your homework spirals. And I am not grading 2.6b, but I am grading 2.5 and 2.6a.
Oh, this is a problem.
Oh, it should be so done by now.
No, see, I have both of those sections done, but one of them's in my spiral.
That you can't find?
Yeah. Well, I have 2.6a.
I'm not checking the section due today. I'm checking the 2 prior ones. I'm just going to put next week for due, because it's not due on Monday, guys.
Yes.
There's homework 15 is the next week? Okay. You guys are grading! And as you're grading, when I come to you, show me 2.5. And show me 2.6a.
If you have my issue,
Yeah, I think I'm just gonna redo it, because I don't know if everybody.
Okay, you can come show me later on today, okay? I'll give you a half right now, but if you can make up, show me, I'll give you.
Right.
Yeah, 2.6. Sending pictures of 2.5 and 2.6. 2.5. Awesome. 2.5. David, you're gonna show me your spiral later?
Yeah, I can come back.
Yes. Just remind me in the email that you copied. Eris, I should charge you. Alright guys, it's count time! Oh wait, were there any more evens? Sorry, one more, 54. Okay, last one on 2.6b, but otherwise open up the composition book because we are going to notes and it's super important that you pay attention, so all other distractions need to be cleared away after you grade the last problem. Guys, this is all on the video, so 2.6b, come Monday with it fully attempted and graded with any questions that you have. We won't take questions today because we did a little more practice. Maybe you needed that, a little more practice. Come Monday with questions on 2.6b. Remind me, because I'm not going to remember. It's after a weekend. If you have any questions, just be like, hey, I have a question on homework number 14, and we'll go back to it. Are those all the evens? Okay. All right, let's go ahead and let's get out of this. Let's go back to notes. Ah! Story time!
Oh.
Yay, don't write it down. Story time.
Copy it word for word.
Ready? Here we go. We're focused in. Our composition books are ready. We're going to section 2.7. It's a big one. 4 days. It's a 4-day one. So some of the kids in BC, it is their favorite type of word problem. So it's not impossible. It's not impossible. In the 1600s, Europe was ushered into the scientific age by such great thinkers as Descartes, Galileo, how to say his name, Newton, and Kepler. These men believed that nature is governed by basic laws, laws that can, for the most part, be written in terms of mathematical equations. One of the most influential publications of this period, Dialogue on the Great World Systems by Galileo Galilei, has become a classic description of modern scientific thought. As mathematics has developed during the past few hundred years, a small number of elementary functions has proven sufficient for modeling most phenomena in physics, chemistry, biology, engineering, economics, and a variety of other fields. One more time, a small number of elementary functions has proven sufficient for modeling most phenomena in physics, chemistry, biology, engineering, economics, and a variety of other fields. An elementary function is a function from the following list or one that can be formed as the sum, product, quotient, or composition of functions in the list. Polynomials, rationals, functions including or involving radicals, logarithmic, exponential, trigonometric, inverse trigonometric functions. With, ready? The last sentence. The differentiation rules introduced so far in the text, you can differentiate any elementary function. For convenience, all the rules are summarized below. You have reached the end of the derivative rules. Now, differentiation is the first semester, so obviously we didn't reach the end of using the derivative rules or applying the derivative rules, but you have reached the end of the derivative rules. Meaning, with the rules that you have in your forever cards, you should be able to differentiate, even though it gets tricky, any function that is given to you from that list, which models most phenomena. Second semester, you will never get to this point for integration. There is no end for integration. Struggle. But differentiation, there is an end and we have reached it. And here is what you guys have learned so far. Now, if I were you, I would take a picture of this. But I wouldn't necessarily write it down in your notes. Because most of these you already have. Most of these you already have written exactly as it is stated up here.
How do they have
Some of them are a little different. What do you see?
I know A to B. Oh, because base. No, we have base. Yeah, I'm base C instead of A.
I have number 7.
Yeah, go team. Number 7 is a good one. And we added number 8. Did you guys add number 8 to your forever cards?
Yes.
Good. We added number 8. What's 1, 2, and 3? 1 is the constant multiple, right? It's just written a little differently. 2 is sum and difference. What's 3?
It's just wait. It's
Product rule. They just wrote first D second plus second D first. Number 4? Quotient rule. Number 5 is just the constant rule. Number 6, power rule. Number 7, we know that one. Number 8, absolute value. Number 9, 10, 11, 12. Those ones we wrote pretty much like it is, right?
Yeah.
13 through 18 are all the trig ones. 19 through 24 are all the trig inverse ones. Woo. The only thing not up there is how to take the derivative of an inverse, but really you just use pre-cal to switch x and y and take the derivative. You just had to talk about it in a section of homework. But with these 24 rules, you can derive any function. And all of these functions model many different phenomena, as it said, in many different fields. What's the point of mathematical models? What's the big deal? Why do you want an equation that can describe what's going on?
Good try.
Because what?
Because God said so.
Because God said so. No, what's the purpose though? Why do you think people ever wanted to find equations that can model what's going on in all these different fields?
So we can explain. We needed it.
Maybe to explain?
Yes.
Maybe to predict? What?
So they needed absolute, so they could apply to every dad.
Oh, okay. Yeah. Or even things like in medicine, if you have a formula that can help you figure out the proper dosage for someone based on their age, their size, their gender, their body weight, that could be pretty important as well. What's a field where you have to know precisely how much, like what dosage to give? Maybe pharmaceutical.
Anesthesiology.
Anesthesiologist is exactly what I was thinking of. Because what do you need to do? Give them enough to keep them under, or else
But not
you can
enough
mess
to
everything
kill them.
else, but not enough to kill them. And they have to play with so many different things, so many different factors. They need a formula for that. They can't get out their clipboard and get out their calculator and start figuring it out as they're in the operating room and the person is starting to come out, right?
Just do trial and error.
That's good. Well, once upon a time, it had to be trial and error, but think about trial and error now. If we were still using trial and error, predictions, are they always solid?
No.
But imagine if we were still doing trial and error. It'd be even worse.
Well, I'm not planning on it.
Be anywhere near
That profession, man, the stress.
I agree too, yeah.
Possible
I don't wanna
lawsuits.
be an anesthesiologist. Yeah, I mean, sure, they get like 600,000 a year, but they sell their soul to do it, so. Wow.
And if they make one mistake.
They're charged with murder.
mostly like pre-thought things? Like it's not like in the
It's not in the moment, not necessarily, unless something goes wrong. Which isn't necessarily their fault, like things can go wrong, it's not their fault.
You can't eat before.
I heard one like places that were anesthesiologists just place it down during the surgery. That was all pre-thought.
That's really funny. It's very possible.
Well, hopefully we'll get to a point where just they sit you down in a big robot and it does all those things.
Yeah, but see, life is unpredictable. Things happen that a robot cannot necessarily anticipate. I'm not sure I'd be okay with that.
Yeah, but I feel like most of the things that go wrong during a surgery are probably due to human error. Like they accidentally like nick an artery or something.
Possibly.
I mean, I don't know about surgery.
I mean, you're modeling, in order to be able to give a robot what to do in a surgery, you would have to have a perfect, like there's a lot of exploratory surgeries where it's like we won't know until we go in. Like you wouldn't be able to program something to deal with that. I don't think.
I mean, unless they...
Wait, did we have to write down that demo?
Not necessarily. I'm actually going to show it to you. Okay. The demo, which one is it? Is it the cone? Okay.
Conical...
Are you guys ready for the demo?
Yeah.
My question to you is, for this illustration, okay? My question for you is, for this illustration, uh-oh, is it not going? Oh, stink. Oh, this is so sad. Oh, there it goes. Okay. My question to you is, are all the different dimensions changing at the same rate?
No.
Does that make sense? Water is being poured in, and as water is being poured in, the tank is filling, the conical tank is filling. But my question is, as the water flows in, is the radius and the height changing at the same rates?
No.
No. And that kind of makes sense, because, okay, if water's flowing in, then question, if it's flowing in at a certain rate, what dimension models water? What dimension? Is that like one-dimensional, two-dimensional, three-dimensional? Water. Three-dimensional. But radius is only technically two-dimensional, because it's a length, so it's in the second dimension. Radius is just a length. It would be measured in something like, what's this say, inches, meters? Something or others? Meters. So these are measured in meters. How can a rate in meters per minute be the exact same as a rate in meters cubed per minute? So the idea is fluid is being pumped into the conical tank at a constant rate, but as the volume is changing at a certain rate, the radius and the height will be changing differently. And even the radius and the height won't be changing the same either. If we were to find the differences between each of these, they are not the same. They're not going at the same speed. So as one is increasing by, what's this show, like 0.2s? As one is increasing by 0.2s, the others are increasing by a little bit less. Or even dH/dt is decreasing. Because as you get higher up on the cone, doesn't the water need to fill more surface area? And so doesn't it make sense that as it needs to fill more surface area, the water can still be pouring in constantly, but it starts rising slower and slower? Or if you guys think of it this way, if you're trying to drain something out of like a funnel, have you guys ever watched it? And it's like, oh, it goes slow, but all of a sudden right here it's like zoom, and it like falls out. Why? Because there's less surface area to cover. So it's able to look like it's going faster, but it's not. It's still pouring out at the same rate. The hole on the bottom, if you were draining it, the hole on the bottom is the same size. Why did it look like it was going slow and then all of a sudden going fast? Because the height changes differently than the volume. All of this kind of leads us up to, I don't think you watched it again, leads us up to this idea of related rates, where you have one situation, but there are different dimensions or different quantities or different variables changing based on that one situation, but they're changing differently. but they're changing different. Here's another example, and this is a really common one. What if I was to do, and I don't have a ladder, I was supposed to, but someone borrowed it and they didn't give it back. That's okay. What if I was to have a ladder against the side of the house, okay? Let's say I'm like painting.
Yay.
And let's say it's not very stable. What's going to happen? I'm leaning in. It's not very stable. The feet were not on the ground strong enough. Am I going to fall backwards if I'm leaning in? No, but what is going to happen? The ladder is going to
kick out.
right? Now,
Good morning.
one situation, the ladder's falling, true? But there's one leg of a right triangle. There's one leg of a right triangle that as the ladder falls is going to get smaller as the other leg of the right triangle is getting bigger. So I'm going to have one rate that's negative because it's getting smaller, but another rate that's getting longer. So they can't be the exact same.
I'm glad you didn't have a ladder.
Yeah, that would be scary. They can't be the exact same, right? Alright, this section says, if they're not the same but they're related, what do we do with it? So it's all about rates. We have movement, we have motion. We know that has something to do with derivatives. We're going to need two review things. Chain rule and implicit differentiation. Chain rule, what do we know? The derivative of something, when the variables don't match, needs to have an extra problem. So if I'm taking d dt, wait, why did I just change it from t's? Time. We're talking about real motion problems or movement problems where the independent isn't just going to be called x, it's going to be called t. So if we take the derivative of something like a y, or if we take a derivative of something, like an x, if I'm basing it on time, x doesn't match either, so that's also going to have an extra u. Or what if it was a v? I'd have a dv dt. What if it was an s? I'd have a ds dt. What if it was an r for radius? I'd have a dr dt. What if it was an h? I'd have a dh dt. Chain rule says take the derivative, but times u prime. Times u prime. You're going to have an extra piece. In implicit differentiation, we know when we have an equation, we're just going to have to deal with taking the derivative of both sides. Taking the derivative of both sides. So the intro. Are the rates of change of each quantity in a situation the same? No. Height could be changing much differently than radius could be changing, much differently than volume of the water being pumped in could be changing. Guys, that's only one example. Technically, I could show you. How many do I actually have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Woo! Everything from airplane to baseball to a ladder, ladder, to oil, to paint, to sand piles.
Just do one more. Shadow.
The AP, who knows what it'll show you. We're going to come back to this example. Which one do you want to do? Shadow? Okay. What's the shadow one? It's a guy walking away from a light pole. Is that what it is?
Oh yeah, that makes sense.
There you go. Sick man starts his walk and a shadow appears in front of him.
Where's the stick man? Oh, he has a triangle head.
So there's a rate of how fast he's moving. There's a rate of how fast his shadow is changing. And one more time, they're not the same.
6 foot.
Even though it's one situation. Yeah, he's a very I think
he's getting extra height from his pointy head.
like Meet the Robinson. Anyway, it's going to the example. But guys, that's there's only. Even though I have like 13 here, that's only a very limited amount based on what the AP can come up with. They can come up with examples of who knows what. We'll talk more about that as
Because
the
they
AP
pay
comes here.
people to do it.
Last year, if you talk to any of the BC kids, bananas and potatoes.
Oh yeah.
They got so mad about bananas and potatoes, but all along I was telling them, who knows what they're going to give you? Tea and biscuits, snow, sand, gravel. I tried to throw at them as many examples as we possibly could, and still they were like, oh, but there were bananas. I'm like, who cares? It doesn't matter. Just do the math. Anyway. Okay, so in this example, let me go ahead and give you some givens. Now guys, do you want to write the whole paragraph? The answer is no. So what do? Whenever we're trying to write down a word problem, I started you doing this last year, you read it, you understand it, and you summarize, right? Read it, understand it, summarize it. Well, read it, summarize it, then hopefully understand it. What do we have? Given the height of the water is changing at a rate of, that's not H equals, that's the rate of H equals, that's dH dt equals negative 0.2 feet per minute. That's the rate or the derivative of height with respect to t. And the radius is changing at, a rate of radius. What do you guys think you're going to call that?
DRD.
dr dt. What are they asking us to find? Find the rate of change. What is the rate of change in the volume? Who's that going to be then, using what I've been showing you?
DV.
ddt.
And don't we need
Such that
don't we need the volume formula?
r equals 1, h equals 2. The question is, what did they not give us but we need to figure out? We have a cone. It's talking about volumes and radii and heights. We just need the volume formula, which is the relationship cone is 1/3 pi r squared h. Kiddos, in the back of your book, you have some geometric formulas that might help you out. Yes. Do we need to review volumes, areas, surface areas of shapes? Yes. But we can do it. We relate the quantities. Wait, pause. What would be my next step? I need derivatives. So what am I going to do to both sides? Derive. And what do you think is going to happen after I derive? Ooh, you better use a product rule. What do you do after you derive? Plug in stuff. And I guess, or I hope, the only thing missing is the thing you want to find. Bye, cool kids. That's the big idea of this section. We're going to have to bust it out because these are word problems. We're going to read, we're going to have to translate, we're going to have to solve. But sometimes you have to find the formula yourself to derive. Yeah. Bye, guys.
What if it's not the only thing that you need to find?
Inversion.
What if
The geometrically, there's going to be a clue that you missed that can eliminate or substitute for one of them in terms of the other. Yeah. Like with the man in the shadow, you have to work with similar shapes or proportion. And then that'll help you tie it together.
Oh, okay.